thank the faculty for choosing me to give this Jones lecture. And it's nice sometimes that when you're part of the faculty here and you talk all over the world about the work you do, you often don't get to talk here. And it's also novel that I can talk on Veterans Day about work that I've done for the Wounded Warrior. So if you look up there, that's me on the left shaking hands with the first Marine that lost his hand and had it replaced by a transplanted hand. And this was him about 6 months later, and it's actually working very well. It works better than if he had cut his arm off and we put it back on. So transplantation, for some reason, works very well, and I'll talk about that today. And this is me on Halloween Day putting a mask on that's just a prototype, a concept for a mask that if I had lost my face to a blast injury and my skin was burned off, the mask would have embedded in it thousands of micro or nano bioreactors and would grow a face back. And that's the kind of project that if you fell asleep for this talk and woke up in 30 or 40 years, then we'd have them out at CVS for you to regrow new skin after you went to Cape Cod. And one of the questions we had was, how are we going to get these devices through TSA? And I said, no problem, because we're having our kickoff meeting in San Antonio on Halloween Day. So it turns out that war and medicine are very closely coupled together. And I've been working on that since around 1995, and if people are interested in how I got involved in that afterwards, they can come up. I'm happy to tell you my stories of how I got hooked up with Navy, Army, Air Force, and other agencies. But what I learned about was something called revolution in military affairs, which I'll talk about today, and how these revolution in military affairs, like the ones going on in the present war, have had an impact on medical innovation. And how in the present wars, polytrauma, which is the result of blast injury when multiple parts are lost, like the recent soldiers when I was down at Walter Reed are coming back with an injury where they've lost both legs, sometimes their penis, sometimes one arm, and their face, all in one injury. And we're trying to provide treatment for that in rehabilitation, which we call catastrophic polytrauma, and I'll talk more about that. And we don't see these things in civilian injuries up to this point. We've had the Murray building blow up, and we ended up with an institute here. We have injuries in civilian, but the injuries in civilian, I'll show you, just aren't what we're seeing in the military. And in the military, it turns out our ability to resuscitate is actually much better than in the civilian world. I'll talk about an algorithm for face and limb salvage and how that algorithm is changing, and a reconstructive ladder, which is plastic surgery's way of organizing how we approach injuries. So I spend every day operating. I operated every day this week, including this morning. On Wednesday, I spent from 9 in the morning till 10 at night reconstructing someone's leg that had a wound there for 30 years. So there's a conventional approach now, and we're changing that approach with the introduction of robotics, transplantation, regenerative medicine, and in some cases I'll talk about this biomask where we're combining simulation robotics and regeneration together. And all this, in some form, is really engineering medicine. So the reconstructive ladder, as you see here, we go from simple closure, like if you cut yourself, all the way up to free flaps, where on Wednesday I took tissue from someone's thigh, took it off the patient, brought it down to their calf, rehooked up the blood vessels, and that's a free flap. And that's 20th century. Now we're adding to this reconstructive ladder, going from simple to complex in plastic surgery. We're adding robotics, transplantation, regeneration to that. And that's what the talk will be about today. So what about this revolution in military affairs? There's been a series of revolutions in military affairs since the introduction of gunpowder and swords. Swords were given up and we had gunpowder, and then we had the Civil War with special rifled bullets. We had trench warfare as we move on. In the present wars, we have these blasts. In the revolution in military affairs in World War II was blitzkrieg. So each war comes up with a revolution in military affairs which provides an advantage to one side over the other, whether it goes back to bullets being introduced against swords, to the present war, where a blast against us has been very effective at injuring our soldiers. And that revolution in military affairs that the enemy has put together with blast injuries has resulted in us coming up with new ways of responding to it, including things like regenerative medicine, new robotics, and transplantation. So when you think about revolution in military affairs, the main example would be blitzkrieg that the Germans did in World War II, where they combined a rapid assault with tanks, airplanes, and communication to overwhelm the Maginot Line, which was seen as something that couldn't be defeated coming out of World War I. And we looked at our military in the present wars as not being able to be defeated, except it was in many cases by this blast that are continuing to occur, especially in Afghanistan. So each war creates new problems that must be met with new techniques. And this is a quote from a plastic surgeon, Richard Stark, in the Vietnam War. But what are the new problems coming out of this global war on terrorism that we've been involved in for 10 years? And it's been a major shift from ballistic injuries, like rifle bullets, to blast injuries. And so we look at starting in 10 years ago with Operation Enduring Freedom, Afghanistan, to Operation Iraqi Freedom, to the rapidly mounting casualty count. So I got involved around 2005 at looking at this. And you can see from these numbers that we keep seeing a growing number of wounded and fatalities. And at present, the overall casualties are approaching 50,000, with 42,000 wounded and 4,500 killed in action. And what's happening here, which is making this even more devastating for the medical corps, is that our ability to resuscitate soldiers that are wounded is so much better than it was in previous wars. So our survival now is 90%. So in past wars in Vietnam, for every 3 wounded in action, 1 would be killed in action. Now it's 9 or 10 wounded in action for every 1 killed in action. And the result is there are more that are severely injured. And we're able to do this better resuscitation through forward surgical teams that reach out into the battlefield to provide high-level care almost immediately, and better body armor that protects the trunk from injury. But it's these shells blowing up below the soldiers that are taking off limbs and faces. And if you look at these numbers, what's dramatic is that as we go across here, and this is the cumulative fatalities in yellow, which is about flat. So this is the fatalities, but the severity of the wounds keeps going up. So they're injuring us with more severe wounds, and this keeps rising, but in spite of that, we're keeping the number that die from these at the same level, which means we have more and more devastating injuries. And this is seen by a comparison of the type of injuries that occur. In civilian practice, people have things like simple amputations or wounds. You fall, you're in a car accident. High energy is a high-speed car accident, motorcycle accident, maybe a gunshot wound. But massive energy transfer is something that really is a war injury from a blast from an IED, improvised explosive device. So these massive energy things cause nerve injuries, cause traumatic brain injuries, bone forms in places it shouldn't form. They cause both peripheral and central damage. So that's a type of injury that we don't see in normal practice. So one of the things the military did early on in the wars is they created a virtual autopsy coming out of DARPA work, the Defense Advanced Research Project Agency, and they looked at every soldier killed in action, and they made a 3D model of the patient and modeled where the projectiles went through and how they were killed to understand better where the failure were in our armor. So here you can see a soldier that's blown up with shrapnel coming up in multiple places. You're trying to figure out what killed them. You can see a map of the body armor they wear. You can see here that there's no shrapnel in the chest area because that's protected. But when you look at the next picture, you can see that they're missing part of their skull. because part of it went up under the chin and blew out the brain. So this is obviously a fatal injury. So as I studied these for the Defense Science Board, and I visited as a consultant at Walter Reed, a term was coined called polytrauma, which is a set of injuries that involve multiple areas of the body caused by blasts, injuring the face, limb, and brain injuries, and also other parts like vision and hearing. And with Paul Pasquina at Walter Reed, we coined a term called catastrophic polytrauma, which are injuries which are really beyond our present methods of treatment of care. So here's the big challenge for this global war on terrorism. Suddenly we're presented with hundreds, if not more, of injuries like people missing 3 limbs and their face that we have nothing in our armamentarium or our reconstructive ladder to treat, and we suddenly need to look at. I was fortunate to be working with the Defense Science Board as a consultant, and they asked me to put together a report in 2007, which took 2 years to do and then 2 years to get cleared by Washington to get published, and it was published this summer. And that report is broken into multiple areas, and I gave it out to the graduate students, but the key area for this talk is chapter 5, which is treatments and technologies. And I'll go over some of those treatments and technologies that we recommended. And versus a lot of reports in Washington, this report resulted in grey teams, meaning groups of doctors sent into Iraq and Afghanistan to look at what the report recommended. Many of those people were on this committee with me, and they went out there. They tried to send me at least once, but a general pulled me off the trip, fortunately. And they looked at what was going on there, and then since then, a number of institutes and programs have been set up to implement many of these things in the report, and I'll talk about some of those. But first, I want to talk about kind of my personal experiences going down to Walter Reed. So I went down there in 2005. I was involved in the following patient that I'll go through, who was in a Humvee and was blown up by a bomb. And this will give you a sense of the present state of the reconstructive ladder, and mostly we'll show by pictures. Here's what he looks like when I got to see him. What happens is he gets the mid part of his face blown away, and out on the battlefield and in the hospitals in Iraq and Germany, they just close everything together. So from the side, you can see all this is missing. So we have to open him up, open up his midface, take his forearm and bone and skin and bring it up and rebuild his midface as a platform. And this is me and 2 of the plastic surgeons at Walter Reed putting this together. So this is a free flap, the top of our present reconstructive ladder, where we take his forearm and bring it into his face just to build a foundation and build a new upper jaw for him. Then what we do is we design a flap on his forehead and bring it down to make him a nose, which isn't very beautiful at this point, but it puts a nose down and builds an upper lip. And then we, over stages, we refine this to make it more and more normal. And here you can see the forearm afterwards. And then finally, this is what he looks like. And he looks more human now, but this is going through probably 20 operations. And the question is, can we replace 20 operations with 1 operation, a face transplant? And we'll show you that work in a few minutes. So here's even a more difficult problem. This is a catastrophic polytrauma. Not only is he missing part of his face and his vision, but both arms. This is the kind of person you see in that movie Hurt Locker, where you get too close to a bomb. He's on an EOD team, explosive device team, so they go out and they defuse the bombs. The bomb goes off and blows away a lot of them. This is the kind of injury you see with a massive energy transfer. So we have the reconstructive ladder put into an algorithm for how we approach this. On the right is what we typically do in the 20th century. We try to salvage limbs and faces, and we do surgery, and we hope with a functional outcome. We choose not to amputate, but to salvage that limb. And we use scoring systems to help us decide which limbs to save and which limbs need to be amputated. And often the key for that is nerve, the nerve final function. So if you have a lower extremity, nerves don't work, often that gets amputated. But if the nerves do work, then we try to salvage that. And sometimes in the blast injury, like we've seen all the way back in the Civil War with causalgia, they have severe pain. If this limb is non-functional, then we amputate it, and then we look here for amputation. We can do robotics, transplantation, tissue engineering, regeneration. And some of the graduate students ask me questions about this, and it's often not this or that, but we'll do robotics now. Eventually we'll do more transplantation as we get away from immune therapy and get to immune tolerance. That'll be better. And hopefully at some point we'll regrow parts. People at Pittsburgh right now are trying to regrow fingertips, and we're trying to regrow in Boston ears. And at some point we'll manipulate the immune system so we can regenerate parts. I tell my patients at Dartmouth that we could get into your genome and find a place in your genome to allow you to regenerate new skin or regenerate so you don't have a scar. But if we did this, we wouldn't know what we control. And I joke with my patients that if we play with your genome, maybe on the way to work, like a salamander, you might actually get out of your car and lay eggs or go find a pond. So we just don't know what would happen if we sort of went to this level. And this is really beyond what we're looking at. We're looking at regenerating tissue by using your own tissue and building through tissue engineering and engineering medicine. So let's talk about robotics. A lot has happened in robotics, and what's happened with the war is the Defense Department, again, has pushed together a revolutionary the arm project to build new robotic arms to match the human arm in performance. And I've been involved in about 16 patients in putting on upper limbs, and involved in going from people that have lost their arms to robotic limbs that work very well. And they have motors in them. They're run by the muscles, so as you think and your muscles send signals, they record those, so they're myoelectric. And people like this that have lost their arm at their shoulder go back to working in the printing press where he lost his arm. So in about 55 to 60% of people, those robotic arms work very well. In more severe cases, this is a woman who graduated top 10 in her class in 2001 at West Point and had her arm blown off by an RPG at the shoulder level. She worked for the Defense Department program to develop robotic arms, and that never really worked out for her because we don't have a good way to attach an arm all the way at the shoulder. So what happened was Jeff Ling at DARPA put together a program called Revolutionizing the Upper Extremity Prosthesis in 2005. And the concept of the program is to develop a brain-machine interface so the arm is connected directly to the brain. The battery life would be 24 hours. It would be durable for 10 years. It would have the cosmetic appearance of normal, and it would match normal motor and sensory function. 2 grants were given out, one to Dean Kamen in New Hampshire, and he called his arm Luke after the Star Wars movie. And then the Advanced Physics Lab with a consortium of other groups put together a project, a longer-term project for robotic arm. In their case, their connection to the brain would be through muscles in the shoulder. These are some examples of these 5-fingered hands, and here's a soldier wearing one. And the concept is to build these arms and eventually connect them to brain implants to run the arms, although the present arms are either connected off of muscles for the one at APL, and the one at Dean Kamen uses foot controls to control the arm, but obviously that won't work with someone that lost their legs. Now, rather than going directly to the brain, people look at whether you can put a head mount on and record signals off the brain and whether that'll have enough fidelity. But for our patient that's missing both arms and legs, what do we do for him? And then the concept is to look at beyond just a robotic arm and going back into warfare, but an exoskeleton like Steve Jacobson's doing with Sarcos and Raytheon out in Utah. So here's a device with hydraulics around the body that you could walk in that could replace parts in your body. So you can imagine this soldier missing arms and even legs wearing this suit, here's Steve Jacobson, and going back like Starship Trooper back into battle wearing these parts. Obviously, this is very cumbersome, it uses up a lot of energy, so DARPA just put out a new broad area announcement. The responses are due on November 15th for a skin that you would wear, and the skin, which would be a thin lining that you can wear under clothes like this suit, would allow you to power and walk, wear 100 pounds in your back, and take that weight and support you, and also shift the weight and the compliance so that you take away some of the torque at your hip, knees, and ankles to prevent injuries from either walking or climbing up or even jumping out of a helicopter. So that's a very difficult task that the President brought area announcement. And what's good about DARPA is they set up hard projects that often don't have solutions, and even if they fail, may come up with interesting solutions that we can look at. Now, what about the face? Dave Hansen has done work on making faces that are very realistic, but no one really has a robotic face. Now, Dave, at a Defense Department meeting, told me that he had a face of Philip Dick, the writer, and I didn't believe it would be very realistic, but Dave said that he has it in the back of the room. This is at the Defense Department in a hat box. So I went back there and had a conversation with Philip Dick, who talked to me, and I could ask him questions because it had artificial intelligence. And then that night, when it flew back by Southwest to Texas, it was lost in the airplane, so no one's ever seen him again. So if anybody's seen Philip Dick's robotic head, please tell me. So that brings us on to transplantation. So what's its role when we look at all this stuff, and what's the trade-offs between replanting a limb versus a robotic prosthesis? And people have done studies looking at this, and generally people choosing between losing one limb and a transplant and losing a limb and robotic will choose a robotic limb. But if they've lost both limbs, they'll choose transplantation, although it'll be more expensive. So I want to sort of look a little bit at what's going on. There's been over 40 limb transplants done and 18 facial transplants done up to this time. At Louisville, they have the largest experience with arm transplants. They've lost one so far. They've done over 10, and they have excellent functional recovery in their arms. And at Pittsburgh, Andy Lee has done 8 arms, and two are unilateral and 3 are bilateral. This is the one Marine I told you about. Here's somebody who's a 4-limb amputee, and these are 2 limbs, so he's been the first person to do the bilateral limbs. Again, they do very well when at the forearm level. If the limbs are transplanted above the elbow, they do much poorer. So that's where we are with arms, and I want to go a little more detail about face transplants. So face transplants are obviously a huge issue, and they're a huge strategic issue because someone goes to war accepting the fact that they may die, and they even accept the fact they may lose a limb. But no one really accepts the fact that they may come out disfigured and lose a face. And here's a young woman that was in a car accident. This is what she looks like after reconstruction. So when someone looks like that, the question is, what can we do for them? So a novel notion is, and this is from Cleveland Clinic and Maria Simonal, who did the first face transplant in 2008 in this country, why can't we take off the entire face from a donor like we do a kidney and put that face onto a recipient? So that was first done in 2005 in France to a woman who had her lower face chewed off by a dog, by her dog, and they replaced it. And I'll talk about that. We now have 18-month follow-up on that. It's a New England Journal article with 18-month follow-up on the first human partial face transplant. Overall, what it says is that she's had really excellent return of function, although it's harder to measure function in the face than it is the hand. She's had several rejection episodes, but she's been very happy with this. Here you can get an idea of what was replaced on her face. So it wasn't the whole face, which has subsequently been done, but quite a lot. The nerves are rehooked up. The nerves have shown excellent sensory recovery. In fact, in one transplant where nerves weren't hooked up on one side, they still recovered. So something about immune therapy and something about the amount of contact surface encourages nerve regeneration. And even more remarkable is the amount of motion that she has with her mouth moving. And here she is looking at her before, after with makeup, and after without makeup. So that's a pretty remarkable change. So what we've seen in at least the first one, and now in subsequently 18, and we're following 5 in this country, that they do very well with satisfactory function. What we're trying to determine is what are the trade-offs, at what point you're willing to trade for looking disfigured for face transplant. And the studies that have been done show that if you take somebody who's middle-aged with 36 more years to live, how many years are they willing to trade off for a face transplant? And the answer is 12 of the 36 years. And what risk of death are they willing to do? And it's 34%. So people find losing their face is a very disfiguring problem that they're willing to trade a lot. And what's happened now is we need more real information. So we've been supporting a program at Harvard, and this is Bo Pomahawk and Elof Erickson, and they're doing one of their face transplants here. And you can see this patient. Here's his electrical burn. He fell onto an electrical circuit. Here he is after multiple reconstructions. And here he is after his face transplant. He's not beautiful, but he's gone from something that's almost not human to something that's human again, which is an amazing thing that we can do. But there's a lot of trade-offs, and one of the things we need to do is study more of them, which we're doing, and also decrease the burden of immune therapy, which long-term can result in a number of problems, including higher risk of cancer, avascular necrosis of the hips, and several other problems. But remember, when we do transplantation, we need a donor. Is there a way that we can just regenerate the part and grow the part? So that gets us into regenerative medicine. And what happened a number of years ago is that Tony Atala, at a meeting in Florida, inspired the military in the midst of all these casualties to say, why can't we regenerate parts for a wounded warrior? And why can't we do this rapidly? So let's create an institute, the Armed Forces Institute of Regenerative Medicine, and do what Tony Atala has done for the bladder, where he's grown a bladder for about a dozen patients that has worked. Why can't we do this for a face, ear, nose, hand, and skin? So this was set up in 2008. It's a consortium that involves partners from industry, the military, the Army Institute of Surgical Research, where I'm doing the biomass problem, the Wake Forest Consortium, and the consortium that I'm chief medical officer in is the Rutgers Cleveland Clinic. Multiple companies are involved, and the areas addressed are limb salvage, craniomaxillofacial problems, burn skin, and scarless healing, meaning can we have a scar and do something to the scar to make the scar go away? If we have scar around tendon repair or other kinds of repair, can we make this go away? And ultimately, Congress lumped transplantation into this, although transplantation fits if you think about some of the things we're doing for immune tolerance. So this was a huge effort, and if you look at how large it was, President Bush, before one of his State of the Union address, looked at the consortiums. About 20 people applied, 20 consortiums, and the amount of money that was going to be given was $42.5 million, and we came in second, but rather than only fund one of the top two, he decided to fund both of them. So they put up $85 million and then subsequently gave supplementals of another $15 million, a total $100 million, to fund a project to look at regenerative medicine for compartment syndromes, limb salvage, facial reconstruction, inflammation, burn repair. And we're approaching now a renewal, so Congress has put away another $100 million to renew this for another 5 years because they expected us to produce one product, and so far there are about 20 products that are in clinical trials. So it's been a big success. Why it's been a success, we don't really know. It's a relationship between lots of different groups. So it's truly a model for engineering medicine in terms of all the different activities that come together to help a soldier here missing his jaw. So if we're going to regenerate jaw with teeth and soft tissue and look at the computer models for that, the polymer chemistry for that, the regenerative medicine, the other engineering, the biomaterials, all this has to come together. And the term regenerative medicine is often used synonymously with tissue engineering, although those involved in regenerative medicine place more emphasis on the use of stem cells. So stem cells has always been our big brand, but it's not stem cells from someone else, it's really autologous stem cells. And many of the investigators in the consortiums that stretch from Boston to California are stem cell experts. So what did a firm say that it was going to deliver? So one of the things it looked at was burn repair. So what happens in the first Gulf Wars if someone had a 50% burn, we decided that they couldn't survive and we were going to let them die. In the present wars, we save everyone. And someone injured in the battlefield is not flown from Iraq to Germany, but we tried to bring them as fast as possible to the burn center, Brooke Army Medical Center in San Antonio. So although most of the soldiers are brought back to the States with injuries in 48 to 72 hours, they come back even faster for the burn. The notion is that we can try to save any burn. But one of the keys is, in 80% burns, how do we grow enough skin? And one of the concepts is that we could do autologous engineered skin substitutes. So we could take a centimeter of skin and in a month grow up a meter of skin and put it back on the patient. So that's what's presently in a clinical trial with Steve Boss. It was aligned with the company Lonza. In addition to the money from a firm, the Office of Science and Technology put in another $18 million to support the clinical work. And you can see kind of an example of that where you have a patient with this much burn, and to resurface that with little pieces at a time takes a very long time. And in this case, you can take a centimeter and grow it into a meter and make that process move much quicker. So that's been a big success for this program. The next area, which seemed even harder, was how can we deal with wound healing and tissue repair and create scarless healing? And one thing that's fascinating has been noted is that if you inject fat into scars, which was noticed in cosmetic surgery, sometimes scars go away. So we have a clinical trial going on right now where we look at scars in patients, whether it's on the face or the limbs, and inject those scars with fat, which is autologous fat transfer, and some of that fat has stem cells in it, to see whether we can reduce the effect of debilitating scars. So there's another clinical trial that's presently going on. And you can see some of that here where you can see a scar here, which is supposedly improved on this side. And this could have a huge impact on patients, not only for skin, but for other areas that we scar, like in tendons. So the program that I'm in charge of for a firm is craniomaxillofacial, which is really a mirror of limb, because in the face we see nerve problems, in limbs we see nerve problems, and skin in the face, skin and limbs, bone defects in the face, bone and limbs. So we came up with a program strategy, which is for very large defects, we look at transplantation, and we emphasize basic science work on immune tolerance. Can we, instead of having immune therapy with 3 drugs, come up with a way to defeat rejection? And someone would say that why should plastic surgeons, for instance, be able to solve such a hard problem? And in World War II, there was a plastic surgeon, Joe Murray, as a young surgeon, who got fascinated by rejection of skin grafts in World War II at Valley Forge. And afterwards, at Brigham and Women's at Harvard, he decided that he'd look at kidneys and did the first kidney transplant in the early 50s and received the Nobel Prize for it. So I think the important thing is the stimulation of the problem and approaching it with certain ways that might be able to solve it. In small defects in the craniofacial area, we look at tissue engineering, either of an ear or a nose or an eyelid or a lip or even small muscles of the hand. Can we grow from the parts? If we take some muscle cells, we take some fibroblasts, we take some nerve cells, and put them together, can we put them in a biomaterial and essentially grow a small muscle unit with nerve and muscle to build an eyelid or a lip? Can we take some cartilage and sample that and then grow it through multiple growth cycles, keep it as cartilage, put it around a framework and make an ear? And ultimately, can we replace other things like bone, nerve, and skin? So when we look at massive tissue losses like composite tissue allografts or limbs, clearly we've been able to now do things like transplant an arm on a Marine who lost it. And this is growing in terms of the multiple centers that are now able to do this. And each of the centers are looking at different ways to try to deal with the problem with the immunology. So we go back to Cleveland, which is part of the Rutgers group. They did the first near-total transplant in America. So these are all the parts that were transplanted. So people ask, how much of the face got transplanted? And it's a near-total face. And it was a woman that had been shot by her husband by a shotgun. after this, this is what she looked like. And it's not perfect, but it's a huge improvement over how she looked before. But the other work that Cleveland is doing is a program where they use TAL-101 antibodies or monoclonal antibodies that can help to take out the T cell population that causes immune rejection and reduce the need for immune therapy. Even more interesting, they're doing chimeric cells where in the donor, they take cells from the donor in human cells and they fuse them with recipient cells. So now the recipient has cells that have two immune systems, the donor and the recipient. And the goal is to put enough of these cells in the recipient so their chimeras, they have two immune systems. So when the donor face is brought to the recipient, there is no need for immune therapy, or at least it's reduced. So that's the kind of research, because part of the AFIRM program, the Institute, is 10% of it is basic science, 90% of it is delivering products to the wounded warrior. So what about replacing parts? Everyone's seen in Scientific American years ago an ear on the rat, and everyone asked what happened to the rat. So we put several $1 million into the rat so that we can grow an ear. And part of the modeling of the ear is to use computer-aided design to do that. So the goal is to grow cartilage, put the cartilage around a framework of collagen over titanium, cover that with skin to make an ear. And in a similar way, we funded a project where people can take models of humans that are injured, build a patient-specific injury model, and then we could CAD-CAM and make parts that are missing and help design the surgery. That kind of tools where we do computer-aided design, computer-aided surgery, help us with modeling the scaffold that we need for the ear. And a critical is stability so that the collagen and the cartilage stay together but still allow you to flex the ear. So here you can see what happens. So here's a soldier missing an ear. So we do a biopsy of cartilage from the other ear, a small biopsy. We grow that up 100-fold. There's a special technique they've developed so that the cartilage doesn't revert to fibroblast but stays as cartilage. And then we can take this titanium framework and cover it with collagen and grow cartilage on it in a bioreactor in vitro. And then once that's grown up as an ear, it can be put under a flap on the side of the head to form a new ear. So that's work right now. Right now it's being done in a sheep. So now instead of rats with ears on their back, we have sheep with ears on their back. So the next step after sheep is you. So the last topic and the most recent thing to be funded is a project that's going on with the Institute of Surgical Research. That's the Research Institute for the military, Northwestern University, the Automation and Robotics Research Institute, University of Texas at Arlington, are all working together in a consortium to develop a strategy for treatment of facial burns. And ultimately, even if you burned off your face down to bone, could we reconstruct the skin, muscles, and deeper layer? And the goal is to combine simulation, robotics, and regenerative medicine. So here's a sort of an artist's conception of it. You put this mask on over a burned face, and in it there's a bunch of nano and micro robotic devices that control things like monitor multiple biological signals, deliver targeted therapy, either stem cells or bioactive agents, a flexible inner lining that can move and shape itself, hard outer shell, and direct interface of the burn. And you can control this at the really sub-millimeter level. So it's really like a conformable skin that has ability to control the fluid, measure the pH, measure the oxygen delivery with a number of sensor units that are all sort of integrated together. And I have a number of more slides that go through each of the different units. And the group in Texas has built a lot of these modules already. The goal is putting it all together. And again, it's a pretty far out notion to do this. And what's nice about some of the military funding is we can, even though we're not going to deliver this in 18 months, we may be able to deliver some subunit of it in 18 months. Of a mask. We already put a mask on burn patients to try to decrease scar. Can we put a mask on that fits better controls the fluid better, to initially be our first prototype, and then afterwards add bioactive agents or even stem cells or other things, because we're already growing skin in vitro and putting it back in the patient. Why can't we move the bioreactors from in vitro to in vivo? So to summarize, we really have a new reconstructive ladder that we're envisioning for the 21st century. The choices were once limited to surgery. The 21st century restoration of function will include multiple new disciplines in this sort of field that we're still getting our hands around called engineering medicine. The modern plastic surgeon, the engineering medicine person, the engineer needs to understand how robotics, transplantation, regenerative medicine come together. What are the choices? One of the people, Andy Lee, working on transplantation, said that all he really wants to see in the future is that a patient has a choice to choose between a transplant and a robotic limb. And the biomask is interesting because it combines computer-aided design, robotics, and regeneration all within one platform. So I'd like to thank especially two people for this. And, one is President Jim Wright, former President Jim Wright, who's giving a talk in 15 minutes, his Veterans Day talk. And he provided support early on in this to hold a number of conferences up here on this topic. He was somebody that I would come to his office and talk to him about work in the Wounded Warrior. I'd come in for a half-an-hour appointment, spend an hour and a half or more in his office discussing this with him. He's hugely passionate about this. And in combination with this, our dean here, Joseph Helbley, has had a real vision for engineering medicine, and coupling that with the Wounded Warrior seems to be a good pairing of a problem with potential solutions that we can create applications. And we've been fortunate to be funded through a number of different agencies to continue this work. So I want to thank you for inviting me to speak today. I was told to go 45 minutes and leave 15 minutes for discussion. So 1 minute ahead of time according to my computer. Okay. Mike.
These are complex issues, and I wonder how the program is looking to include the person receiving this complex technical care in the decision making.
So the couple ways we're doing it. So I'm running a different program called Biomedical Translational Initiative. And in that program, we're doing things like taking fat and reconstructing craniofacial defects. In that program, there's 14 patients so far before our Wounded Warriors. So we've been trying to reach out directly to the Wounded Warrior. The problem is the way you get a Wounded Warrior is through their provider and their commander, not directly to the Wounded Warrior, because that's the way the military works. So we recently had a meeting with all the providers at Walter Reed National Medical Center, which is the new Walter Reed Bethesda. So we're working more closely with the providers down there and trying to gain their confidence, the colonels that are providing the care to these, so that they're more comfortable referring patients. In the group with the fat transplants to the head, we already had a patient withdrawn from that study by their provider who felt that that fat graft would interfere with further work they were having done on their jaw, which didn't make sense. So it's critical that we work closely. That's why it was helpful for me to spend a few years consulting at Walter Reed, working with their plastic surgeons. The problem is you work with them for a few years and they rotate out. So then you have to create new relationships with the new people. But the key ends up being working with the provider, and then they get the patients to see it. And the other thing is we have one soldier that wants a face transplant, but he wants to be the 13th one in this country. So we're up to 5, and he says, I'll come back when you've done a few more. So they're a pretty sophisticated audience, and they're watching our results carefully to see whether or not we can deliver on our claims.
You noted that the outcome for artificial limbs for amputation below the elbow is much better than above. It's understandable. What I'm wondering is, rather than cases above the elbow, rather than connecting to chest tissue, muscle movements, and that sort of thing, there would be a possibility of growing hand or finger tissue in the region of those nerves up at the chest and then connecting to those as an a more sensitive way to connect signals to
Yeah.
the lower part.
So I think that we're at Rehab Institute of Chicago has been putting transponders in up in the shoulder area, at least on the motor side, to try to sort of jump that gap.
That's using the gross muscles of the chest. I'm
Yeah.
wondering whether you could grow muscles and nerves similar to those in the hand in that region where the nerve trunk is terminated, and whether it would connect properly up to that, so
Yeah.
that you'd have much finer control.
So the short answer is we've not thought about that, but I'll run that by the team, but I'll make sure I give you credit. So, more questions?
Questions? Well, if I may, I'll ask one myself. We talked about that just before the noon seminar. Do you not feel that by lowering the casualty rate by having very effective medicine, we're also, in a way, lowering our threshold for agreeing to go to war and making it easier for politicians to decide to go to war?
So it's interesting. So this has been studied extensively by RAND. And RAND studied not just the recent wars, but wars over the last 50 or more years. And they find that there are kind of 4 determinants of you as a public, what you're willing to accept from the White House when we go to war. And one is the White House has to tell you that the war has some value for national security. The second interesting one is the White House has to convince you that there's some likelihood we could even win the war. Because the public, even if it's important, doesn't really want to go to war if you can't win it. Then the significant thing here is that the third area is blood and treasure. How much is it going to cost in the lives of our soldiers or the wounded soldiers? And how much is it going to cost out of your pocket for us to do this? And then the fourth one I found fascinating was partisanship. A Democratic president going to war with a Democratic Congress has an easier time doing it than with a Republican Congress, and vice versa. So it turns out that if you look at these, look at the curve, whether it's small wars or large wars, it works out pretty well. So one of the jobs of people like me as a doctor is to just try to treat patients and shift disability back. So we reduce disability by treating them earlier, and I have a slide on that I didn't include. But by doing that, I allow the president to go to war with essentially a lower threshold. And it's actually, if you know more about war, because I've studied it for 15 years, there is a strategic casualty that we coined in our report, which means that just 100 soldiers missing their faces may be as important to discourage you from going to war, meaning the public, as 1,000 killed in action. Because we kind of accept killed in action. And we always say, well, 40,000 people die a year in car accidents. But we don't see that many people in car accidents that are so disfigured they've lost their face. So these are injuries that it's very difficult for anybody to accept, and they have a huge impact on our ability to go to war. So you can say that that's good, and we shouldn't transplant them because we should leave them around as reminders of what it means to make this kind of choice. Or if we can fix them all, maybe we'll have a lower threshold for going to wars earlier. You'll find in most military meetings, this is not the discussion. Our job is to come up with treatments. And in fact, in this case, one of the things that we talked about, because I was not only on the medical chair of the medical panel, but I also was one of the advisors to the Joint IED Defeat Organization. So on either side of me were generals and other senior people. And we looked at operational versus medical things. And we found operationally we could deliver things in 18 months or less if we needed something. If we needed something to defeat a new bomb that they were delivering, we had a rapid way of moving it out to the battlefield. But we didn't have the same thing for medicine. So I raised my hand and said, why can't we somehow more rapidly deliver products and devices in the medical field, which is what A-Firm has done, and even this other program I've been running, BTI, has done better. So essentially, we were committing ourselves to getting treatments out even faster, which is what doctors need to do. But there's the other side of the coin, which is by doing that, we influence. Most doctors don't understand how we influence. I really understand how we influence because I've read the reports by Rand and the strategists to understand this. And I think the enemy has read it too, because the enemy has, over time, created certain injuries that almost speak to the fact that they could have killed the soldier, but they didn't. They maimed them in a way that has a greater impact on us. And it's hard to know that for sure. That's a hard experiment to do. But you wonder sometimes in terms of how they understand our culture better than we understand their culture, which I'm convinced of. But that's another discussion. So, any other questions? Jim Wright's talk just down the way, right? Rockefeller, yeah.
Well, thank you, Joe, for a very